Hello everyone, this is the 8th lecture in real analysis and we are going to talk about relations and functions. So the plan is to define a relation and give an example. We will also define the domain and the range of a relation. We will define what is a function and provide some examples, and we will talk about the domain and the range of a function. So before we proceed further, let us recall that for non-empty sets x and y, the Cartesian product x cross y is the set of all ordered pairs, little x, little y, such that little x is in capital X and little y is in capital Y. So this is called the Cartesian product. So for example, the Cartesian product of the set of real numbers with itself is the set of all ordered pairs A, B, such that A is a real number and B is a real number. And we often denote this as R squared, and we call it the plane. So the graphical interpretation of the plane is when we have two axes, two perpendicular axes, x and y, and we have points A and B, such that the A coordinates is on the x-axis and the B coordinates is on the y-axis. So the set of all of such points A, B on the plane is the Cartesian product R cross R. So let us now define what is a relation. So let x and y be non-empty sets. A relation on the Cartesian product x cross y is merely a subset R of the Cartesian product x cross y. So for example, let us consider this relation S, that is a subset of the Cartesian product R cross R, that is defined as follows. S is equal to all of the ordered pairs x, y, such that x squared over 2 squared plus y squared over 3 squared equals to 1. So you may have learned in Calculus 3 that this equation here is the equation of an ellipse, and on the y semi-axis is equal to 3 and the x semi-axis is equal to 2. So this is the graph of this equation, x squared over 2 squared plus y squared over 3 squared is equal to 1. So just in case you didn't know this, you can take my word for it. So this relation S is the set of all of the points on this graph. So now let us define the domain and the range of a relation. So as before, let x and y be non-empty sets. Let R, a subset of the Cartesian product x cross y, be a relation. So the domain of R, which is denoted by domain of R, is the set of all elements x in X, such that there exists y in Y, such that x, y is in R. The range of the relation R, denoted by range of R, is the set of all elements y in Y, such that there exists an x in the set capital X, such that the ordered pair xy is in R. So for example, let us consider the relation S that we considered before, that consists of all ordered pairs x, y in R squared, such that x squared over 2 squared plus y squared over 3 squared is equal to 1. So as we mentioned before, it is this ellipse over here. So let us try to understand what is the domain of the relation S and what is the range of the relation S. So if we take a point xy on the relation S, so on this ellipse, then the x-coordinate of this point will be here. And so you can see that as we exhaust the points on the ellipse, the x-coordinates, they range from -2 to 2. So the domain of the relation S is the interval from -2 to 2. So as we try to understand what is the range of the relation S, we need to look at the points x, y on the relation, and we need to look at their y coordinates, which will be here, right? So if we look at the y coordinates of the points on the relation, we may notice that they exhaust the interval from -3 to 3. So the range of the relation S is the interval from -3 to 3. So let us now define what is a function. So as before, let x and y be non-empty sets, and let f subset of the Cartesian product x cross y be a relation. So we say that f is a function from x to y and denoted as follows: f column x arrow y. So f is a function from x to y if the following two conditions hold. The first condition is that the domain of the relation f is the entire set x, and the second condition is that for every x in capital X, there exists a unique y in capital Y such that x, y is the element of the relation f. We denote this unique y as y equals to f of x. And so we can depict a function as the following diagram. So suppose we have a set x here and a set y. So for every point x in the set x, there exists a unique element y equals to f of x in the set y, and the function f gives a correspondence between x and f of x. Another diagram that can help us to understand what is a function is the following. So suppose we have input x, an element of the set capital X. Here we have some box, some operation, which is a function f, and on the output, it gives us the value y equals to f of x in the set y. So for example, we can consider the function f from the interval -1, 1 into r, defined by the formula f of x equals to x squared. So f can be written as the relation of all of the ordered pairs x squared, where x is a number from the interval -1, 1. And we can plot this function on the plane r squared as follows. So it's going to be a segment of the parabola. So all of the points on this portion of the parabola belongs to the relation. And let us try to understand what is the domain of this function. So the domain of this function will be the set of all of the x coordinates of the points on this portion of the parabola. So you can see that the x coordinates range from -1 to 1. So the domain of the function is the interval from -1 to 1. And we could have written that immediately because that's how the function is defined, right? So the function f is from -1 to 1, so that's its domain. Let us now understand what is the range of this function. So the range of this function is the set of all of the y coordinates of the points on this portion of the parabola. So you can see that these y coordinates, they range from 0 to 1. So the range of the function f is the interval from 0 to 1. So another example is the function f from the interval 0, 1 into r, defined by the formula f of x equals to x squared. So you may notice that the formula for the function f of x equals x squared is the same as in the previous example. What is different in this example is that the function f is defined on the interval 0, 1. So actually the domain of the function is a part of the definition of the function. And so the two functions in the previous two examples are actually different functions. And we can confirm this by looking at the graph of the function in this example. So it's just this portion of the parabola that is defined on the interval 0, 1 of the x-axis. And we can see that this graph is different from the previous graph in the previous example, which was a different portion of the parabola. So the next example is asking us to determine if the graph that we see is the graph of a function. So let us recall what is a function. So the definition of the function that we gave in this video can be summarized as follows. So a function is a rule that to every x in the domain puts into correspondence a unique y in the range. So the word unique here is very important. So let us draw a vertical line here on the graph. And we can see that this vertical line intersects the graph in 3 points that have the same x-coordinate that we can denote by a, right? So these are points a, y1, a, y2, and a, y3. So to one x-coordinate a, there corresponds 3 y-coordinates, y1, y2, and y3. But we must have a unique y-coordinates corresponding to a given coordinate x. So this graph is not a graph of a function. So the answer is no. So this last example gives us an idea to formulate the vertical line test. So a curve on the plane R2 is the graph of a function if and only if every vertical line intersects the curve at most once. So let us use this vertical line test to determine if the three curves depicted here, the curves A, B, and C, if they are functions. So if we could look at the curve A, if we draw a vertical line here, we see that the vertical line intersects the curve at 2 points. So this is not a function. So this is not a graph of a function. If we look at the curve B, if we draw a vertical line, no matter where we draw it, the line will intersect the curve at most once. So the curve B is a function. So it is a function. And finally, the curve C, if you draw a vertical line here, it intersects the curve at 3 different points. So it is not a function. So this is all for this video. I hope you liked this video. Please put a like underneath it. Please subscribe to this channel, support this work, and be good at math.